there.
Oh, okay. Yeah, so we are discussing earlier, myself and Christopher, probably like last couple of hours. Uh, One of the things we and noticed that, and I especially noticed over this break period, rethinking about the history of physics, is that conservation laws. I think that's what we're talking about. And we'll have probably, if not next week, the following week, about the thermodynamics and the Maxwell equation, episode 2. I'll be very specific about what they achieved, and then we'll talk about our interpretations. I think one of the things that we finally were able to square out, and then we are still debating, is about a conservation laws. The energy conservation applies for thermodynamics. We know the first law of thermodynamics is about the energy conservation, but the other conservation that probably they derived from Lagrangian transforms like that, the mathematical thing, is about the momentum conservation. And that was the problem that Maxwell took up. He came with the idea of field. And then, however, there's a problem with the velocity distribution, things like that. But of course, the, the force is not constant. So what exactly field is, these started becoming a big problem. And then the quantum physics says, even the rotational momentum is not conserved because of radiation of charged bodies like electrons. And then Einstein came that, yeah, the mass itself doesn't remain constant, it changes. So he threw the whole idea of conservation momentum into fray, and still we are dealing with that. And now, instead, uh, the quantum theory came with correspondence principle, I think, and then the relativity came up with the equivalence principle. That's about it. But the conservation law is still up in the air, and then the standard model and all these things are trying to find out a way to reconcile to that. So
So, do you
that's
think
where we
that
are, and
if
then
mass was constant, would that solve the, or would that would help in
yeah,
in trying to solve?
yeah, or, yeah, it could, yeah, it could, yeah,
But
like Christian is doing, Christian, yeah.
in order to do that, well, I know there was some experiments done in Fermilab where they were looking for an increase in mass as they send the particle around the accelerator,
Uh-huh.
and they couldn't find any. But and so their conclusion was that in order for the equations to work out, like Einstein's special relativity and all that, so in order for that to work, they suggest that time just slows down for the object, so it never reaches the speed of light. So it's not that mass increases; it's that time slows down. But that's been a long-standing argument between relativists. There's been these two camps, and it's clear that the people at Fermilab who conducted the experiment, I think, might have already been in the camp where they were like, there is no such thing as mass increase. I don't know why I think that. I just get the impression that that was the case. And then I think there's people in the other camp who think that mass does increase, like a lot of the people at CERN. And I think, I don't know if they've ever conducted an experiment, but all of their research is based around this idea of mass increase. So I wonder who's correct. I mean, if they did the experiment, they got a null result, that should be accepted as the correct answer, right? Until,
Oh, yeah.
I mean, obviously somebody has to repeat their experiment in order for it to be completely above board. But still, it is, if it's the only experiment of its type, then, I guess it's up to other people. If people have a problem with the idea, if they don't like it, then they should try and repeat the experiment. Obviously, there's people at CERN who are clearly on the other side of the argument, so they should, maybe they're not even aware that this experiment was conducted, or they're too busy looking at other things to bother, or maybe they don't have the capacity to do it. So those are all potential arguments. But so if it was the case then that time was the factor which prevents mass from changing, and therefore could offer kind of a life raft to this idea of momentum conservation, But do you think that if we had time sort of changing in that way, then and that being the deciding factor, do you think that that would help or hinder ultimately finding momentum of conservation? Would it be this? Would we be in at the same problem in a different place, if you know what I mean, or a different place, or different problem but the same place, or whatever?
Yeah.
Do you have any thoughts on that? I mean, is that
yeah?
Is
So
that a way of this, or
I'm doing the time aspect now. The time is being vector and scalar. So I have some published, JPS. So I am looking at the conservation, and I
right?
have come up with the analysis of the conservation of the time aspect.
Yeah.
Condition under which. So the time itself, that vector time or the algebraic time, is second derivative of the action. We know the action is the fundamental thing. So it's a second derivative with respect to their space coordinates.
Okay, so
So and then
time is a factor in it. So if the time basis or the time dimension, let's say, is changing while you're trying to do your derivative, that's going to be a problem, right? I mean, is that something that you can account for, or
yeah,
does that break the system, or what happens?
yeah. Actually, that's the whole question. Much like the field, the dimension of time itself is a question. Is it a dimension? In abstract.
I'm just using the term dimension loosely. You know, the way if we have a data set.
I know. Yeah. So in that case, if you lose in a loose definition, the time has rank 6, which means almost like 6 dimension, virtual dimension.
That is your specific research, though, right?
Yeah.
Right.
Yeah.
And
so,
but what? Time, so I don't know.
Yeah.
Okay, and that's fine. I mean, you should talk about your own research, but I'm just wondering.
The momentum,
So
conservation.
Do you think you could solve it using your idea, or is it connected to?
Oh yeah, so that's how I'm coming around it. Can we tag in with the momentum? See, that's the next step. Can we tag in that time aspect with the momentum and see at which point the conservation can occur? It could be a derivative of the momentum, things like that. And we know force is a time derivative. But if you take a space derivative of the momentum, right, instead of the time derivative, so we got a different direction. Can we show some kind of conservation, much like Lagrangian? So we may have to come up with a Hamiltonian or Lagrangian and then come up with the momentum equation, and then you find the space derivative and see doing the similar thing like we do with the Lagrangian, same kind of manipulation, derivatives and calculus on them, whether we can prove something is the momentum or some derivative of the momentum is held constant. So if we can prove that, I think, it could be the second derivative, for example, of momentum. I don't know what that is. Or connect momentum with the action. That's another possibility. Then if you connect momentum with the action, then I can use my time thing. You know what I mean?
Right. But so let's say you have some conservation law. So essentially, when one value is up, the other value is down, and vice versa. Yeah. So if we have a momentum problem, and so the object is moving, and it has initially it's still, and it has inertia, and then you have to overcome that inertia to get it moving, and then when it's moving, it has momentum, and you have to overcome the momentum in order to stop it, right?
Yeah.
So it's a kind of a conservation law. Inertia and momentum are equivalent, yeah? They're the same.
In a way, yeah.
Right. They're the same thing in opposite directions.
Yeah.
So could there be a conservation law embedded in that somehow? It seems like you'd have to ignore space-time coordinates, and you'd have to. What's that thing called where? I think quantum mechanics is background dependent and in general, and general relativity is background. Oh no, the other way around. General relativity is background independent, is it? Whereas quantum mechanics tends to be background dependent. Like it factors in time and space into it in derivatives and stuff like
Yeah,
that.
because the speed of light and all that. Yeah.
Okay, so but then you're talking about using, a specific time basis of space and time in this derivative. So in a sense, then you've got a background dependent system. So you're leaving out relativity and all of that. But then, so then if you include it, you've got you've got a different kind of conservation system where when the momentum is one way, time is moving at a certain speed. And when the momentum increases, time moves at a different speed. So the trade-off is in the time or in the mass, right?
Yeah.
So there would be, why isn't that a conservation then? And
yeah, I mean, like Planck's law is kind of like a conservation, like energy times time. If you integrate energy with, you get a Planck's constant, right? So there is a constant. So in the same way, like energy, regardless of what you do, is conserved in the sense of a system. So your total energy of the system remains constant, right? So that's a conservation of energy. The same way, momentum, if you multiply by time, for example, and that's a constant, right? Then in that case, that is momentum times time is a conserved, you know. So we can come up with that. So something like that, it could be something like that.
yeah, and then I mean, there's the issue of time itself. Like, you're talking about conserving energy, and then this relationship between energy and time, which kind of it goes to the Heisenberg uncertainty principle. If you try and figure out how much energy you have in the system, it will take the more accurate you want to get, the more time you'll have to spend. So there's this trade-off. But then you could ask, maybe there's a conservation law within the structure of time, because hey, well, if we can conserve energy, and then we should have a conservation law for time.
That's what I'm coming up with. Yeah.
Right. So
in a way, indirectly.
Yeah, of course. So that'd be interesting to know what that is. But what I'm thinking is, you could look into concepts like fractal time or something, where you have a certain amount of time, which we call the present, let's say. But then if we take smaller and smaller snippets of that time, like femtoseconds and even smaller, that is still the present moment. And that is the actual present for that present moment. So, so there could be like a kind of a sense of some sort of fractal thing, that the whole moment is contained within that tiny moment somehow.
Like Planck time, for example, could be a Planck time, for example. It could be, we can think of a Planck time, and that is conserved. It could be conserved in that regime. You know what I mean? So that's okay.
It's conserved because is it conserved through Heisenberg's principle? Because you spoke about the Planck length or something, or H, is it H bar or H to do with
Planck or momentum times delta x times delta t or something like that, right? That Heisenberg.
The difference in energy,
position and time, or momentum and time, things like that.
Well, is it not? The difference in position times the difference in I think it's times the position.
If you measure accurately the position, we cannot get time accurate. I mean,
no. I think it's it's a time. I guess it's a time issue. Like, time is a factor of the thing that we can't understand. It's either, well, in one sense it's speed, but it's really velocity. And in fact, I think, and another interpretation is we're really talking about momentum, because there's a mass to whatever's moving. So it's position and momentum is the Heisenberg uncertainty principle. Then another one is energy and time is another one. So those, can you mix the two? Can you get cross-quarter things like position and time?
Energy and time, if you find a small fraction of time, then you can equate to Planck's constant. So in that sense, energy is not much of a problem. Momentum is. in the same way position is. If we measure time accurately, we don't know exactly where it will be. Like electron measure accurate time, we don't know electron exactly where it will be. So that's like a cloud. We think it is there. We see
Right, but
probabilities.
you can work out. You could use a very narrow window of time to find its momentum, or no, you could use a very narrow window of time to find out its position, but you will lose information about its momentum. If you take a very wide amount of time, you can figure out its momentum accurately, but you'll lose the information about its position. And that generates this kind of curve that goes like this, I think, with time up here, or position and momentum down here. So then they take the middle part of the curve to say, this is the best we can do in terms of accuracy.
Yeah.
You know, we minimize the error from the momentum side and we minimize the error from the position side. So we just get halfway. And that number is Planck's constant.
Yeah. Or H bar, what was.
So it is, yeah, I think you're right. So then so that's what I was asking when you're talking about getting down to the Planck length. Is it related to this idea that we're now like H bar?
Yeah. So yeah, I'm working the discontinuum physics with Emery Taylor, and then I was kind of we were trying to communicate because he's very specific, he's very accurate in what he does, so he doesn't move away from it. So recently with my, I mentioned that he's looking over my time thing, paper and everything. But I mentioned that the discontinuum length, we think that discontinuum length is the smallest length, and that is like 10 to the power minus 26 is c times the Planck constant. So that is the 10 to the minus 26 or so. That you cannot go anything smaller than that. That's what we think. So this discontinuum length is actually a little larger than the Planck length. So anything less than that, you cannot go anything less than that. So everything, the real space has to be in terms of the discontinuum length. So that's the minimum you need to have the observable universe.
Hello, sorry, can you hear me? Does that not rule out the Planck length then as a length? If you can't go below the discontinuum length, then surely the Planck length is no longer a thing.
Yeah, Planck time. It should be Planck time, not Planck length.
Oh. Okay.
So Planck time times the c is the discontinuum length. So Planck time 10 to the minus. Yeah.
Planck time times c.
Yeah.
Okay. So yeah, I mean, I don't see the reason why I don't really discuss this stuff. I don't really understand or know. I don't know much about this whole discontinuum physics. I've read a bit about it, like come across it here and there, and I think it seems like a very complicated thing. I think I might have mentioned this before, actually, that one of my big problems with they like, well, if we're trying to find a sphere in space or something, sometimes physicists will use discontinuum to like denote a volume of space that's distinct from another area of space. And maybe it works, maybe it doesn't, but there's something about it that I find very loose and a bit irritating. So, but then there's another issue I think that is maybe more pertinent or something. So if you have a spacecraft and it's accelerating, and then so you have the light cone of the spacecraft and all of this, and there's something about tying that, like, what is the pocket or something of the spacecraft, like as it's moving, and when events happen, how quickly do they happen or something? So what is the discontinuity between the spacecraft and the original space as it's moving or something? Was my basic understanding of it, but I found that even that's a bit vague. I found it a bit difficult to grok, I suppose is the right word to use. So do you have any clarifications on that I need?
I think the environment is important. See, the medium which is moving, is it superluminar? things
But
like
in
that is
general, we
important.
say no, right? Because we're talking about general relativity, and that usually precludes superluminal movement. So just within the framework of relativity, where this whole discontinuum comes from, right?
Problem is the time dilation. For example, if it is here, if it is in one position and then it's moving to another position, spacecraft, right?
Yeah.
So it's moving from here to here.
Yeah.
What happens to the time itself? Because in that, how fast is moving? Is it close to the speed of light? The spacecraft?
See, this is what I don't remember. I think does it even matter? Like,
Yeah, it matters.
Let's say the spacecraft begins to move. I mean,
if it is a small velocity compared to speed of light, I don't think anything much happens. I don't think there'll be a large scale time dilation or anything like that.
Yeah, that makes sense. Of course. Yeah. So let's say but I'm just wondering, because like, let's say that the spacecraft begins to move. You think it would need to accelerate up to the speed of light. But of course, that's just theoretical because, according to Georg, nothing can go that fast. So let's say it can accelerate to the speed of light instantaneously or something. Or let's say okay. So is there some sort of minimum time or length then?
Yeah, I think they will be.
There has to be discontinuity maybe between space and time on the craft and the space and time outside the craft. And this is as much as I understand. I've also heard about this rock that's floating through space. Is it?
Yeah.
There's some rock that tumbles in a chaotic way or something, and it's doing that because I think that's a quantum decoherence problem, though. Anyway, that might be a separate issue then. So let's continue with this point about the spacecraft.
Yeah. So if it is looking at that, and let's say instantaneously it moves to the speed of light.
Okay.
So in that instance, that it is at rest, and then suddenly it gets to the speed of light. Is there a distance that it covers? That's the whole question. Instantaneous means it's happening at the same place.
Yeah, that's a good point. Yeah. Well, so if it's instantaneous, then there is no distance, right? And if there's no distance, then there's no time. So it's just happening instantly.
So that's the question of instantaneity is the whole question here. That's the instantaneous. Really, the thing is that everything, in terms of equation of motion, everything takes space and time. How do you accelerate? So it means that transverse and longitudinal. That's the only way we can think about it. So something is happening in that direction to make it. It can oscillate in this direction to the same direction transverse. You can oscillate in that direction to get to the speed of light, maybe instantaneously, and that is instantaneous because we are measuring the longitudinal thing, and with respect to the longitudinal thing, is instantaneous because longitudinally it's not moving, only transversely it is vibrating, whatever, and then get to the speed of light, and then it moves on longitudinally. That's a possibility. We are considered that we have like 10 papers, and many of them are now loaded onto RG with Emery Taylor. And then he does argue about this aspect that there's for electron, for example, there's a charging cycle. And I did the math also, the charging cycle for the electron. And then the charging cycle doesn't move any place. Then instantaneously gets the speed of light, and then it moves. And so the charging cycle, it vibrates, whatever it does, vibration or whatever, transversely until it gets speed of light, and suddenly then moves at the speed of light. So that's instantaneous with respect to the longitudinal motion.
Right.
So space cat could be very similar thing. Space cat could be here at this position, and it could be doing vibration, whatever it does, until the speed of light. And at that instant, it gets the speed of light. Then it moves. So that movement, then it is discontinuous because it moves here, then it moves here, then it charges again, and so on and so forth. So it keeps moving in a discontinuous fashion. you know. But how much time it takes for charging, things like that, we don't know. How instantaneous. So
But
it's
isn't
a
the whole
transverse
point
and longitudinal.
of
So if you are
discontinuity?
looking at the
The whole point of discontinuity is about, like, you have an object in space that has
yeah,
a light cone or something, and then
yeah,
you have another object which is outside of that object's light cone,
uh-huh.
and that's the is that not the discontinuity? You must be talking about a different discontinuity then.
Yeah, we are talking I think we are talking I think longitudinal discontinuity, I would think. But we are not
Well, that was another thing
transversal.
you mentioned about longitudinal and transverse waves achieving greater than light speed. I thought that was impossible for those waves. Scalar, like a scalar torsion wave, if
Uh-huh.
you like want to refer to it that way, that could have instantaneous transmission, but you couldn't have it with a longitudinal wave because then you're talking about like an electromagnetic wave, right?
Yeah, but it could have a charging cycle, the transverse. So it doesn't move until it gets some energy, enough energy, you
Yeah.
know. So it does some charging cycle type of thing, you know. So it has charging cycle, and so it doesn't move, and then moves instantaneously once it gets the speed of light.
Oh, okay, that's
So as far,
interesting.
so if you look at longitudinally, it's always moving at the speed of light. It's
And
not
do you have
instantaneous.
any reason to believe that such a thing exists?
Well, even Andreas Michaud has pointed out this in his theory that that is quite possible that because it has self-propagating property, electromagnetism. It
Right.
doesn't. It doesn't. It has its own power. It is self-powered. So in the sense that it doesn't need anything outside external power or force to activate it. It has internal things that helps it to charge and gives the energy and keep moving, keep moving. So it generates its own energy in that sense.
Yeah.
So the
Okay.
electromagnetic, yeah. So that's a self propulsion.
Okay.
The
But
electromagnetic.
yes, but then you have this idea of like, if we think of the idea of a quantum, particle, like let's say when the photoelectric effect. So if you hit, let's say a silver atom or something, or an electron,
Yeah.
and you just give it a small bit of energy, you won't get any photons emitted. But if you give it enough energy, then you get this
Yeah.
photon. But then if you increase
Yeah.
it a little bit more, you don't again. And
Yeah.
so then it's just describing this kind of quantum wave
Yeah.
packet thing where you need to get up. So it's like, so does that mean that energy is in quantum bits, or does it mean that
Yeah.
you have to get up to a certain threshold and then so it's like a capacitor which just emits?
In a way, you can think of, yeah, that's a good point. It's like the LC circuit. LC circuit.
You've got a particle that you're saying that sits in the same place and doesn't move until it gets enough charge, and then it moves at the speed of light. So, okay, so that's interesting in terms of what we just talked about there with the photoelectric effect. But do we have any evidence of such a thing? Like, what is that particle? It would have to be a photon, would it? Because if it's moving at the speed of light, it's got to be massless.
Yeah, photon. So electron to photon, like electron, and when it emits the radiation, it becomes a photon. So electron is sitting in its orbit.
Is the radiation it's emitting is the photon though?
Yeah, so it becomes a photon. Electron becomes a photon.
Okay, but if an electron emits a photon, we don't say that the electron has become the photon. We say that the electron emitted the.
Oh yeah, no, it jumps. Like electron is jumping from one orbit to another. So in that jump, the energy difference, becomes, is released as in the form of a photon radiation.
Okay, so it hasn't become like the electron didn't change into a photon.
No,
but
not at that time. Yeah, but the electron is not. See, if you distinguish the electron in one orbit, is not the same as the electron in another orbit. Suppose in terms of
Well,
energy.
two different electrons, is it? One in one orbit, one in the other orbit.
Yeah, I would think so, because how do you distinguish a particle? The particle is distinguished or characterized by its energy, right? So if it has one form of energy, that electron, I would distinguish energy of one electron versus energy of another electron to be separate. They are not the same type of electrons. But
Okay, that seems reasonable.
that is the, I think we'll avoid the confusion.
Yeah, well, yeah.
I think so. But
so the
at
question.
the same time,
So you're saying that when we talk about an electron in an orbit, and then you keep adding energy to it, and then it hits a threshold and it jumps into the next orbit, and as it does so, it emits a particle which now travels at the speed of light. So that entire system you've just described there is what you're talking about when you're talking about this discontinuum physics.
Yeah.
But what you're just describing there, though, is just basic, or electron moves from one orbit to another. Like, how does it? What's the new aspect? Why refer to this as discontinuum physics? And what's
in the sense that continuity, the continuum mechanics doesn't hold there. It's not the continuum, like the field itself is not a continuum, in the sense that you cannot say point 1 and then it goes to 0.0009 or things like that. So 0.1 to 0.10001.
It's not
go like that.
You're talking about a discrete thing, like a quantum thing, which is what we're talking. Electrons, photons, orbital shells. It's quantum, but we already know that. I'm just wondering, what is the new thing about this that distinguishes it from either A, the quantum, or B, maybe just A, really, because that's what we're talking about, I think.
Oh, that's because right now the quantum says the cloud is a probability function. That it depends on the wave function collapse, so to say. In the sense that when you measure it, it is there. When you don't measure it, it's not there, kind of thing.
Right. Yes.
We are not saying, discontinuum says that's not the case.
Okay.
Is that you try to measure it? Suppose, it's an example. We are not put that in the paper yet, but I'm thinking aloud, and I'll be discussing with Emery, because he's very laser focused on that, so he knows exactly. So if I see something else, he will immediately refute that. But so that's good thing, because I also think in many different ways, about quantum and astrophysics. So, but I do the math. I can do the math, and you can check. So that's all working fine. So the thing is that discontinuum is like, suppose I have discontinuum, trying to measure. Suppose I measure here, I can exactly find that. But I am in between the discontinuum line. I don't find anything. So that's the thing. So it's not a wave function collapse itself. It's because of the discontinuum aspect that I am not able to measure it.
But wait a second. If you measure in between something, then you should find it. I mean, you're still making
anything.
You're still making a measurement, so the collapse should happen. You know what I mean?
That's what quantum mechanics says. But what we are saying is that time, like we say, for example, what you call the double slit experiment, whatever, the diffraction pattern, where it sometimes you see as a wave, sometimes you see as a particle, right? It's one of the fundamental things.
Well, no, that's not. I understand where you're coming from there. I can see where your thinking lies. That's not actually really correct, though, is it? Because they fire one particle at a time through the slit. And if they are measuring which slit it goes through, then there's a collapse. But there's also this, there's this interference, really, which is the main thing, right? So, oh no, sorry. If they don't measure it, that's the point. It goes through. It goes. It goes through both slits, essentially, is what they're saying, or something goes through both slits, and interferes with itself, and then creates the pattern. But that pattern is built up one particle at a time. So it's not as if there's all these, all the particles are there, and you can just measure the spectrum of the interference pattern, and then say, well, okay, we were going to take a measurement here at the minimum part of the interference pattern versus a peak point, and then say we get a collapse at the peak because there's a particle there. We don't get a collapse in the trough because there's no particle there. That doesn't happen because the whole point of the peaks and troughs is that they've occurred because we didn't measure anything. But then you could say that when it hits the screen, that is a measurement, right? So there's a collapse happening at that point. But there is no peak and trough, per se, because we cannot observe that in the system. It's only after multiple iterations of the experiment that that will become apparent. So I don't.
Yeah, but the quantum mechanics, what does the quantum mechanics? It says that when you measure, they collapse. The peak and everything collapse so that it's there. If we don't measure, they remain distributed as peaks and troughs.
Right, yeah.
This is what quantum, but we are not saying that.
No. Yeah. Well, but in the light experiment, the slit experiment, it's a bit different, isn't it? Because if you do measure, then you get one pattern, which is just a normal interference pattern, I think, which is more spread out. But if you don't measure it, then you get an interference pattern, which is actually more discretized in a way, if you think about it. Because there's gaps between the bars. I mean, obviously it's more spread out in terms of, a scope. Yeah. But it's kind of more discretized, isn't it? So that's interesting.
So there's inconsistency. Yeah, there's inconsistency in the quantum mechanical explanation, I think, in that sense. But the discontinuum, what we are saying is that there is no such thing.
The explanation is just what we observe, because we.
Yeah, but a measurement problem.
But it's
why should it be there only when we measure? Suppose you are there. You are there only. It's like saying.
But more to the point, so like if I'm calling the interference pattern discretized, that's just because that's how I see it. That doesn't actually mean it's discretized or in a quantum sense or in any kind of sense that's meaningful. It's just how it appears, So, but yeah, anyway, it's interesting, but I don't know.
No, it's like saying, like you are there, but only if I see you there, that you exist. If I don't see you, you don't exist there. But it's something like that. If I don't measure you or seeing you like measuring you, right? So then you are there. Otherwise, as far as I'm concerned, that's true. From my point of view, that's true. I'm not sure whether you are there or you are home or I'm not sure, right? You could be in many different places. So multiverse does make sense to me from that point of view, in the sense that if I don't actually measure, if I don't actually see you, it could be anywhere. You could be here, you could be in Belfast, wherever you are, different places. And I don't know exactly where you are until I talk to you and you tell. So I get information. That's correspondence, in some ways. Like I talk about that in one of the papers in Canadian or the OJPS. I do talk about a correspondence, like within a mile radius or something it occurs. And when you are in that region, we know exactly happening. But we are far away from it. Somebody has to like television or something has to transmit to say what's going on inside that, what event is going on, or somebody is present or not. So I get that information.
I
don't know exactly.
There's two theories, isn't there? There's the kind of, what you call the pilot wave theory, and would be in one camp, and then maybe the Copenhagen interpretation in another. So you've one that's saying, we are dealing with like specific things that exist at a specific point.
Broglie or something,
Right, yeah. And then the other one would be that it's a probability function and that it doesn't actually exist until we measure it. So, but I think there's reasons why they're suggesting that kind of outlandish thing.
Yeah,
and
sure.
Right. So, and ultimately, it seems that we just don't know because of how small this area is, and that we can't get information out of it. Because of the uncertainty principle and all of these other things, we just wind up
resolution.
with
it's a question of resolution.
So the mathematics works in a way that's probabilistic. But yeah, so I think to upend that, you would need like something really phenomenal, you know.
Oh yeah.
Yeah. So I'm not going to approach that because like at the moment I wouldn't, because it's such a big deal. That's like a really
but this continuum looks at totally different way. You know what I mean? So that's what we are trying to. So far, we are able to explain these things, and Emery is very particular more than me in looking at that. And if you tell him something, I mean, eventually, I think what I'm saying is that if we get our thing, he also gets approved. So he may want to practice that here. We'll see. We will practice our thing for the conference.
Well, we did mention that about possibly in the future, Emery would do a presentation here. He didn't get back to us.
Yeah.
Also,
maybe that
people as well, Brandenburg and stuff.
It could be that
he heads to the manual, but I think the issue is like, we kind of broadcast here, but we mightn't get a lot of viewers. So I think some of these people do check the viewer count, whether they will come on and speak. But that's missing the entire point of this channel, which is merely just to archive stuff. We're not specifically here for view counts. If you're an attention whore, we don't want you. I know, I'm joking.
I mean, see what Christian also, and that
we're fine as well. We're open to all people. So one thing, so we might leave it there. But next week we might not be on. The week after, we might have you with the second installment of the history of physics. Is correct?
Okay. So you are taking a break.
We don't know. So I don't know about next weekend. I don't know. I could be traveling.
Yeah.
Or I could be here. So we'll play it by ear.
Yeah.
You shouldn't schedule anything specific for that, unless you want.
Let us know.
Yes.
Like to Wednesday, Thursday, and based on that, we'll either schedule it or not schedule it.
Yeah.
But if it is, I say, since we are not sure, I'll prepare it, but most likely it will be 2 weeks from now, the episode 2. Most likely.
Right. Yes. And then, that works well.
I'll try to keep everything ready. So even the last moment, maybe I will be able to present. But I most likely, even if you are next week, we'll have similar things we discuss. And then if you want to discuss something about the conference also, we can do that, or other things, like we are doing today. We can do that. So that's not a problem.
Yeah, we can discuss even off there. But so I think we'll leave it there, and we'll chat about that. Okay, see you later. Bye.
Thanks a lot. Have a nice week. Okay.